In the last video, we saw what the post-correspondence problem was. In this video, we're going to present a proof that it is, in fact, undecidable. This proof is rather long and tricky, and so before we get started, let's talk about a couple of definitions. First of all, remember that we can represent the state of a Turing machine in the middle of its computation with something we call a configuration. At any one point in time, a Turing machine is in a given state. For example, it might be in state Q7. And at any one point in time, the non-blank portion of the tape contains a number of symbols, and the tape head is positioned over exactly one of the cells or one of the symbols. This is the entire state of the Turing machine at this moment in its computation. We can represent this with a configuration string, and one way we can do that is by listing all the symbols in the tape and inserting the state directly before the symbol over which the head is positioned. So this particular configuration of the Turing machine would be represented by this string. So in a computation, we move from one configuration to the next. So each of these C's, C4, C5, and so on, is one configuration, and at every step in the computation, the Turing machine moves from one configuration to the next configuration. And at the end of a computation, the Turing machine halts in an accepting state or a rejecting state. So an accepting computation history is a sequence of configurations, like I've shown here, such that the first configuration in the sequence is the starting configuration, where we're in the initial state and the head is positioned to the left of the first symbol on the tape, and the tape contains the input string to the computation. And the last configuration in the history shows the Turing machine in an accepting state. And each step in this computation history is a legal computation of the Turing machine, so it moves from one configuration to the next, following the rules of the Turing machine operation. We can also have a rejecting computation history, which is exactly the same idea, except the last configuration would show a rejecting state rather than an accepting state. A computation history is a finite sequence of configurations. If the machine does not halt, then the sequence of configurations would be infinite, and we say that there is no computation history. So by definition, the computation history only exists if the machine ends with an accept or reject state. For deterministic machines, there is at most one history on a given input. For non-deterministic machines, we can have many histories corresponding to the various branches in the computation. The non-deterministic choices can lead to different configurations and different computation histories. From now on, we're going to assume that our Turing machine is deterministic. So what that means is that given a particular input, there is either an accepting history or a rejecting history, or there is no history if the machine loops. The theorem that we're trying to prove is that the post-correspondence problem is undecidable. This is a rather lengthy proof, but let's start with an overview of the proof so we can see where we're going. This is an example where we're doing a reduction from the acceptance problem for Turing machines to a post-correspondence problem. This is a little bit different now because the problem that we're looking at is no longer something about Turing machines, and it comes from a completely different domain. So we'll see how we can use Turing machines and the acceptance problem for Turing machines and the undecidability of that to get to a proof of the undecidability of a problem that looks on the surface quite different than a Turing machine. So remember that if a a string is an element of the acceptance problem for a Turing machine, then that string, which encodes M and W, means that M, when it computes on W, would accept. Okay? So, given a particular instance of the acceptance problem, which means given a particular Turing machine M and some string, if that instance is part of the language, in other words, if that string is accepted by the Turing machine, it means that when you run that Turing machine on string W, it would accept. And in particular, there would be a computation history that describes that computation. A finite computation history describes the computation of M on W. So if we're given a particular instance of the acceptance problem, we're given the pair M and W, and what we're going to show how to do is encode that into an instance of the post-correspondence problem. So given a Turing machine description M and a string to run that Turing machine on W, we're going to encode that into an instance of the post-correspondence problem in such a way that there's a solution to the problem, to the post-correspondence problem, if and only if there is an accepting computation history. So this idea of computation histories will be used in this whole proof idea. So if we could decide whether this instance has a solution, then we can decide if there is an accepting computation history. And by extension, it means we could decide the acceptance problem for Turing machines. But of course we know that that's undecidable and we cannot decide that. So our proof is complete, our proof by contradiction is complete, and we prove that in fact we cannot decide the post-correspondence problem. So now let's turn to the details. Remember that an instance of the post-correspondence problem consists of a number of tiles, or dominoes if you want to call them that. And I've represented them a couple different ways. One way is like this, which looks a little bit like a traditional domino. Another way is with brackets. And I've also represented the tiles this way, okay, where instead of having something on the top, I have an A column and a B column. So however you do it, it's fine. And then I've also shown solutions like this. Okay, here is a tile with 1 0 1 1 1 on top and 1 0 on the bottom. Okay, that's the tile that's represented up here. And there are some other tiles, and this is a solution because when you line the tiles up together, all of the symbols on the top strung together is the same string as all the symbols on the bottom strung together. Okay, now let's look at Turing machine configurations. Remember that a Turing machine configuration looks like tape symbols with a state embedded in it, and implicitly the assumption is that the head is positioned on the symbol directly to the right of the state. Now we're going to represent computation histories like this. So let's look at this more carefully. Let's just assume that our initial input to a Turing machine computation is 1 0 1, and of course we start the computation in the initial state at the left end of the tape. So if that's our input string 101, then our initial configuration is going to look like this. And what we're going to do is we're going to represent a computation history as a sequence of configurations that are separated by the pound sign. So we're going to have a special symbol, introduce a new symbol to the alphabet, and it's going to be used to separate the configurations. And we're searching for an accepting history, which means that the last configuration in the computation history will contain a state that is the accepting state. And on my slide, sometimes I draw, here I've indicated the accepting state is Q sub A. Other places I represent it as Q sub accept or Q ACC. It's the same thing, I just wrote it differently. So that's a computation history represented as a string. Our proof is a proof by reduction, which means that we have to present a way to reduce the acceptance problem for Turing machines into an instance of the post-correspondence problem. In other words, given an instance, given a string that we want to know whether it's a member of this language A sub tm, okay, we need to show how to turn that into an instance of the post-correspondence problem. That is our reduction. And again, we know that the acceptance problem for Turing machines is undecidable. And if we assume that we can decide the post-correspondence problem, then we could use that to solve the decidability of the acceptance problem for Turing machines. And so we get to our contradiction that way. But the point is, in our reduction, we are given an instance of the acceptance problem. And that means we're given a pair MW, where M is the representation of a Turing machine and W is an input string. In our example that I'm going to work through, I'm going to assume that the example input string W is 101. Okay, so we're given a machine and a string, and from these we need to give our reducing function. We need to show how to take those two things and construct an instance of the post-correspondence problem. Remember that what an instance of the post-correspondence problem is just a collection of tiles. So we need to create a collection of tiles. So given an M and a W, we're going to show how we can produce a collection of tiles, such that if you could find a solution to this post-correspondence problem instance, then you found an accepting computation history, which proves that M would accept W. And so a solution is going to look like this. This is kind of the main picture that shows our acceptance, our post-correspondence problem solution. And so here I've shown on the top a string and on the bottom a string. And I've indicated that we're going to use tiles. Like here's the first tile, pound sign on the top, and pound Q0, and then www. So, or more precisely, whatever string W is, we create a tile. And in our case, our initial W is 101, so perhaps I should have said 101 here. So here you see that tile in action, being used as the initial special starting tile. So we're going to create a bunch of tiles. One of those tiles is going to be the special starting tile, shown here. And here is the beginnings of a solution to the post-correspondence problem that we're creating. And notice that the string on the top exactly matches the string on the bottom. Okay, we follow through and everything matches just right, at least as far as I've drawn it. And these strings are computation histories. So you see a number of configurations separated by pound signs. And let's just look at the bottom string. The top string is identical, so let's just look at the bottom string. And what this configuration says is that we're in state Q0 with 101 on the tape. And now let's assume that our Turing machine has a transition that goes from Q0 to, say, Q4. And it reads a 1 and replaces that with a 1 and moves the tape head to the right. Okay, so for that particular transition, we're going to create a tile that looks like this. And we'll see how this tile works, but basically it says if you're in state Q0 looking at a 1, okay, which is when this transition would be taken, then you go to state Q4 and you move over. So now, in this particular case, you write a 1 So here we're writing the 1, and now we're positioned to the right of that 1. So we can see that on the top is information about the previous configuration, and on the bottom is information about the next configuration. And here we're using that tile right here. Okay, Q0, 1 on top, Q1, Q4 on the bottom. And notice that they're kind of all offset by one configuration. So the top of this tile matches the previous configuration. It must match the previous configuration. So if we were in Q0 to the left of a 1, then we could use this tile because the top of the tile would match that part of the configuration. And the bottom of the tile ends up going over here on this part of the string, and that builds the next configuration. And we'll see that we have tiles to copy over the 0, to copy over the 1, to copy over the pound sign, and so on. So now let's look at all of this in a little bit more detail. In the previous slide we saw how we got from state Q0 to Q4. Let's look at a couple more transitions. So let's assume that this is our Turing machine, or at least part of it, with states Q4, 5, and 7 shown here in a couple of transitions. Of course, remember, we're given our Turing machine as well as the initial input string, and we're trying to construct an instance of the post-correspondence problem. So given this Turing machine, what sorts of tiles are we going to create? Well, I'll show you that in a second, but first let's see how the computation history works. So when you see the tiles, it'll make sense. So let's say we're in state Q4, and now we're positioned just on top of this 0. Well, this transition says read a 0, replace it with 1, and move to the right and go to state Q5. So that's what we did here. We replaced the 0 with a 1, and we moved to the right. And then this next transition says, if you're looking at a 1, change it to a 0 and move back to the left. So we are looking at a 1 in state Q5, so we replace it with a 0 and we move back to the left 1. So from here we move to here. And so now we're looking at this 1 here. And we go on and on. So let's look at this transition from this configuration to this configuration. Okay, we're reading a 0 and replacing with a 1 and moving to the right. Okay, and so we're in our tape is 101, and so that's where we are here. And so 101 with Q4 looking at the 0, and so this outlined in dark red is showing the tile that we would use next. The tile, well, actually it's showing several tiles. One tile matches 1 to 1, okay, and just basically copies this 1 over. But this tile right that we're interested in with Q4 to the looking at the 0, with just to the left of the 0, it replaces the 0 with 1 and moves the state 1 cell to the right and changes it to Q5. So with 3 different tiles, we can copy this configuration over to this configuration. So this is showing how we use our tiles to look at the previous description, to look at the previous configuration by matching up against whatever's in the string so far from the previous tiles, and then adding some new information to the bottom string, okay, and then later tiles, of course, will match that, and from there we'll go to Q7. Okay, so now let's look again at all the tiles that we're going to create. Given a particular instance of the acceptance problem, namely given a Turing machine and a starting string, we are going to create a number of tiles shown on this slide, and one tile is the special starting tile that we will create as part of our post-correspondence problem instance. And it looks just like this with pound signs where you see them. The initial state, followed by whatever the initial string is, whatever the input string W is. Okay, so there's our special starting tile. Now, for any transition in the Turing machine that moves to the right, it goes from some state to some other state. It reads some symbol and replaces it with some other symbol. So, for example, from state Q to R, reading an A and replacing it with a B, we would create a tile like this. In state Q, looking at symbol A, we replace the A with B, move to the right, and go to state little r. For left moves, such as this one right here, we're in state Q, and we go to state R again. We read some symbol A, replace it with B, but this time we move to the left. Well, we need to create a tile that looks like this, where we are in state Q looking at an A, we replace the A with a B, and then we move to state R and move to the left one cell over whatever symbol was to the left of the Q. So we don't know what symbol that is, so we need to create a bunch of tiles. In fact, we need to create one tile like this for every possible character in the tape alphabet. So for every C in gamma, for every tape alphabet character, we're going to create a single tile with these symbols on it. And finally, we need some tiles to basically copy the rest of the tape. So for every symbol in our tape alphabet, we'll need a single tile that just copies from the previous configuration to the next configuration the character without changing it. So we can use as many of these tiles as we need to copy the other parts of the tape that are not next to the tape head. And we also need to copy the pound signs over. So we have a special tile to do that job as well. So let's see how this works. So we're given a Turing machine which has a bunch of transitions and a bunch of states, and we look at that Turing machine, and from those we create a whole set of tiles. For every for every transition that goes to the right, we create a tile like this. So here's an example of a transition that reads a 0 and replaces it with a 1 and goes from state Q4 to Q5 and moves the tape head to the right. So we create, for this transition, we create one tile. And here's a transition that moves to the left. It reads as 1, replaces it with a 0, and goes from 5 to state Q7. And for this transition, we need to create one tile for every symbol in the alphabet. Here, since we need to move Q5 over to the left, we need to move it past whatever symbol is here. And so we create a tile for 0 and a tile for 1. Here we're assuming our tape alphabet just consists of 0s and 1s. Now, let's look at how some of these tiles can be used. So, let's assume we're in state Q4, and we're going to make the transition to Q5 and then to Q7. So, look at the configuration down here at the bottom. We see we're in state Q4, looking at a 0. We change it to a 1 and move to the right. Okay, we change it to a 1 and move to the right and go to state Q5. And then we're looking at a 1. We change it to a 0 and then move to the left and go to Q7. So we're looking at a 1, we change it to a 0, move to the left and go to Q7. Okay, so you can see the sequence of configurations, how they are correct and legal configurations in a computation history. On the bottom string, we're seeing the legal configurations. And we're also seeing how the tiles are used to go from the current configuration to the next configuration. So the top part of the tile matches this configuration. Looking at the transition from Q4 to Q5, the top part of the tile matches this configuration, and the bottom parts of the tile give the next configuration. So a tile like pound over pound just copies the pound sign. 1 over 1 just copies the 1. And any other symbols that are on the tape get copied likewise. And then where the head is, we copy and make a few changes to change to a new state and replace characters. And so in that way we've gone from state Q4 to Q5 and made a change to the tape. And then in the next part of the configuration history, we match the tops of the tiles to the previous configuration with Q5 and so on. And the bottoms of the tile are shifted over to the right to give the next configuration in the computation history. So I've shown how we go from one configuration to the next configuration in the computation history, but we're looking for an accepting computation history. So how do we do the accept? Well, we have to complete the match. Okay, we have to make the top string and the bottom string match. So we need to add some special tiles to let this happen. And so we're going to add special tiles, as we show next, to allow the accept state, once we reach it, to sort of eat the symbols on the tape, if you will. So from the accept state, there are no transitions that leave the accept state, of course, because once you enter the accept state, the Turing machine stops. But for the accept state, we create 4 special tiles, or more precisely, for every symbol in the alphabet, we have to create a couple of tiles. And what these tiles do is effectively get rid of everything else on the tape except for the single state, Q accept. So let's look at these. They're all quite similar. They have Q accept on the bottom, and if there's a 1 to the left of the accept state, okay, or a 0 to the left of the accept state, or a 1 to the 1 to the right of the accept state, a 0 to the right of the accept state, a 1 to the left, or a 0 to the left of the accept state, we can use these tiles. So let's say we're in a configuration like this where the tape is 1, 0, accept state 1, 1. Well, we could use one of these tiles. For example, we could use this first one where there's a 1 to the right of the accept state. Okay, so I've shown that right here. Okay, and look at what it does. The accept and the 1 match here, but in the next configuration, that 1 has been eliminated. Okay, so now we just have 1, 0, 1, 1, 0, 1. So the use of this tile, in some sense, allows this accept state to eat the symbol just to the right of it. And the rest of these tiles allow the accept state to eat, if you will, the symbols to the left and right of it. And so you can keep applying these tiles until you gobble up all the other symbols in the configuration. Eventually, nothing remains except the Q accept state in the configuration. So here I'm showing the very last step. Okay, here we have a configuration with the accept state and only one single symbol left, a 1 to the left of the state. And we apply the tile that eats that, and then we're left with a configuration between these 2 pound symbols that just contains the accept state. So we use the pound over pound tile to copy the pound here. Now this last tile, Q accept pound pound over pound, is this tile right here. So we add this final tile, this special final tile, to finish off the match. And so at that point you can see whatever we got before here, we finally use this last tile to complete the match. And if we can reach the accepting state in the computation, then we can find a solution to the post-correspondence problem. So let's review what we've just done. Let's review the proof. If we can find a solution to this instance of the post-correspondence problem that we've created from the given Turing machine and input string, then we found a legal accepting computation history. which shows that M accepts string W. And our question is, does a solution of the post-correspondence problem exist? Well, if you could decide the answer to this question, then you can decide whether M accepts W. Okay, if you could know, given this post-correspondence problem, whether there is a sequence of tiles that will form a solution, then you would know whether there is an accepting computation history. So that would allow us to decide the acceptance problem for Turing machines. In other words, to determine whether M accepts W, we encode it into this instance of the post-correspondence problem by creating these tiles the way we've just described, and then we determine whether or not a solution exists. And if the answer is yes, a solution to the post-correspondence problem exists, then we know that M accepts W. And if the answer is no, there is no solution, then we know that MW does not accept W. So if we could decide whether there is a solution to the post-correspondence problem, yes or no, without looping, then we could decide whether M accepts W, yes or no, without looping. But of course we know that the acceptance problem for Turing machines is undecidable. Therefore, we've proven that the problem of finding a solution to the post-correspondence problem is in general undecidable. Although, of course, as we showed with our examples, in some cases we can find a solution, and in some cases we can prove that there is no solution. But in general, finding a solution to the post-correspondence problem is undecidable. And that completes our proof.